All right, second lecture about the Fourier transform. I had told you in the previous one where it comes about mathematically and what its properties are. Now let us consider physics. Imagine we are tuning a bell. We want it to sound at exactly the right frequencies, and we do that by shaving a little bit of material there and here until the frequencies are what we want. So there's a bell that we are tuning. One of the ways of measuring the frequencies in a bell would of course be what you would as chemists consider a natural kind of spectroscopy. We put a speaker next to it and we sound every wavelength in turn onto that bell. When the bell begins to resonate, what will happen is, because the mechanical movement will be involved, the bell will be absorbing the energy and converting it into heat. So if we put a microphone here and start listening into the volume of the sound that comes through, as soon as we hit the resonance of the bell, there will be absorption of the radio waves. In this case, acoustic waves. So if that's the absorption and that is the frequency, we will see perhaps a bunch of peaks at the frequencies that the bell is resonating at. This, however, is quite a slow process. We would need to shine every frequency in turn. We would need to wait long enough for some equilibrium to be established in there and slowly crawl through every frequency. And there's quite a lot of frequency range in the at least audible acoustic spectrum. What the actual bell tuners do is something different. They take a bell and they strike it with a hammer. And of course, from what you've just seen in the previous lecture, you know that the resulting oscillation, so that is some amplitude, let's call it E, as a function of time, it will be some complicated oscillation. From the content of our earlier lecture today, you perhaps can guess that this will be related to that by a Fourier transform, because it is Fourier transform that extracts individual frequencies that are present in an oscillatory signal. So our job today is to put some formal physics on this and to demonstrate that this is in fact strictly true, that for certain class of physical systems, the pulse response, here represented by a hammer strike, is related to the frequency response by the Fourier transform. So item 1 for today, linear time invariant systems. Consider a black box. We don't know what's inside, but the box has an input and an output. So some function f of t, some signal, goes in, and some function g of t goes out. The black box is called linear if it mathematically behaves linearly. That is to say, if we have at the input some f1 of t with some coefficient alpha 1 plus some coefficient alpha 2 f2 of t. So if we give it a linear combination of inputs, we must receive the corresponding linear combination of outputs. So alpha 1, the response to the function f1 individually, plus alpha 2, the response to the corresponding input. So if we know that the black box returns something in response to f1, returns something else in response to f2, then if we mix the two input signals, we must get the corresponding mixture of the outputs. And for example, this is the case for an acoustic amplifier. If you give it a mixture of signals, it amplifies them equally. It keeps that mixture in. So this is called linearity. The second property we would require it to have is time invariance. which means that this system responds in exactly the same way today as it had yesterday and as it will tomorrow. So if we give it some input, f1 of t, and it returns us some output, g1 of t, then what must be the case is if we shift that input in time, f1 of t minus t0, we must get back the correspondingly shifted output, g1 of t minus t0, by the same amount. So that was called linearity, this is called time invariance. And let us study such systems. In a lot of cases in physics and chemistry, for the input signals that are sufficiently weak, a lot of physical systems behave as LTI systems. You will see that if you do courses in chemical engineering, where we actually have at least 4 lectures on design and analysis of such systems. Now, let us do spectroscopy on that system, so we can fit different waves into it with frequencies omega, so signals of the kind I omega t. And we need to find a mathematical form, a function that corresponds to a hammer strike. And this is something, as chemists, you may not have encountered before. It's called a delta function. It's been introduced by Paul Dirac, so relatively recently in historical terms in mathematics. And delta function is the following interesting beast. You have the coordinate system, you have this time t, and you have this delta of t, and it is 0 everywhere, so it goes like that, except the origin. And at the origin it is infinite, so goes to infinity. However, it goes to infinity in such a way as to have the integral minus infinity to infinity delta of t equal to 1. Not forgetting the dt here. So it is an infinitely sharp peak, but nonetheless of a finite area. So imagine, for example, we had a Gaussian here, like that. You know that Gaussians have a certain area. We can normalize it to have a unit area. We can make it a bit sharper, like that, but allow it to keep the same area. We can make it sharper and sharper and sharper. Of course, it will become taller and taller and taller. And in the limit of infinitely sharp, infinitely tall Gaussian, it converges to a delta function. And these delta functions, they've got one other useful property. If you have some other function here, so let's say this will be our f of t, and we multiply it by the delta function, so for example like that, so this is our delta of t minus t0, and this time is t0. Think about what is going to happen when we do such a multiplication. Almost everywhere, this function will be multiplied by zeros. The only place where it will survive is at this cusp of the wave function where it is infinite. But this infinity will be multiplied by the value of the function at t0. And so a property which we will now make use of is that if we take an integral minus infinity to infinity f of t delta of t minus t0 dt, what it does is it cuts out the value of this function at the peak of the delta function, so this is f of t0. So this convolution property, when you convolve a function with a delta function, you get the same function back. So far so obscure, but we will now put this function to good use and just literally make use of that property. And as you've encountered this beast a few times in this course, it will become a bit more clear exactly what is going on here. Okay, so the first thing we are going to do is we will feed that hammer strike into our linear time invariant system. So what I'll do is I'll say, okay, our phi of some delta function, right, what is it going to be? Well, to do that, I can use that property there. So our phi of some arbitrary function f of t, let us replace it with this representation here. So I will have a phi of that integral, so minus infinity to infinity, f of some t prime, then delta of t prime minus t dt prime. Okay, remember that phi is linear, and of course the integral is the limit of a sum, and so I can take phi inside. The second thing I will notice is that for the purposes of the integration here, t prime is an integration variable, right? It is not a function of time. What is a function of time is this delta. So what I then have is minus infinity to infinity f of t prime, then phi of delta t prime minus t dt prime. And that is an interesting property. Notice what this tells us. This f is arbitrary. This delta is specific, right? We know it, it's the hammer strike. And so this phi is the response of the system to the hammer strike at this time. And let's call it h here. So whatever this response is, it will be h of t prime minus t. And that is actually the property of just the system. This is called a pulse response. This is a response of our physical system to a hammer strike. And then this is just an arbitrary signal. And so we arrive at a very interesting property that the response of an LTI system to an arbitrary input signal is determined by just one thing. It is determined by its response to the hammer strike. If we know its response to the hammer strike, we would be able to reconstruct its response to any other input. And this is really quite a general conclusion. And this gets us halfway to where we want to be. So the first thing is our response to an arbitrary function, f of t, is the convolution. This integral is called convolution and occasionally denoted by a star, is the convolution of a f of t with the h of t, the pulse response. Okay, so far so good. This is the hammer side of the bell tuning process. Let us now consider the spectroscopy side and feed one by one individual frequencies into our physical system. So our phi of an oscillatory signal, so ei omega t, as per the property we have proven here, so we literally just use that integral there. It's an integral from minus infinity to infinity. I've used t prime here. I think I've used tau in the handout. Doesn't matter, but let us just do that. So we have ei omega t prime, right? So this is our input signal, and then this h of t prime minus t dt. Reminds you of anything? That looks like a Fourier transform, doesn't it? So let us do a little bit more arithmetic here. What I will do is I will shift the time. Notice this is t prime and that is t prime minus t. So what I'll do is I will multiply and divide by the exponential of I omega t, because the integration variable is t prime. That would just be a constant for the purposes of the integration, and so we can do it. So we will have then e I omega t, e I omega t with a minus sign, that integral minus infinity to infinity e I omega t prime, and then h of t prime minus t dt prime. I will pull this one with the minus inside the integral, and then we have e I omega t integral minus infinity to infinity, then e I omega t prime minus t, and h of t prime minus t dt prime. But notice this is an integral that has been time shifted by t, but your limits are infinite. You're integrating over the entire set of times anyway. It doesn't matter whether you've shifted the function or not, it will get integrated over regardless. And so we can replace that and that by just t prime. So what we have then is e I omega t integral minus infinity to infinity e I omega t prime, h of t minus of just t prime now, dt prime, and that is a Fourier transform. The one with the inverse here, but a Fourier transform nonetheless. Right, so ft. But notice that we also got our original signal back. We gave it this oscillation, it returned us this oscillation and multiplied it by some number. And we will call that entire thing h of omega. So that is h of omega times e I omega t. One frequency goes in, the same frequency comes out, multiplied by a number. And for that reason, this is called frequency response. And this is, in fact, the absorption of sound that our instrument here is going to see. So some frequencies get attenuated, others are not. Okay, and we have, in fact, just proven the physical property that we had set out to prove, that the frequency response of the system, so the frequency spectrum of the bell or the NMR spectrum, is the Fourier transform of its pulse response. And this is why a lot of electromagnetic spectroscopies can operate in the pulse mode. You know how NMR spectrometer works these days. We give a short, sharp pulse. We record the ringback called free induction decay. We Fourier transform it, and we get the frequency spectrum. Well, this is why we do the Fourier transform, and this is why we get the frequency spectrum. This is, in fact, a general property of any linear time-invariant system. Not just spins, but also, for example, bridges. If you would like to know the resonance frequencies of a particular engineering structure, what you do is you bring in the microphone and a hammer, and you smack it with a hammer and you record the ringback, and those are the resonance frequencies of the structure to a pretty decent approximation. Okay, so summary of the picture so far is that the pulse response of a physical system, when you Fourier transform it, gives us the frequency response, and this, as you know, is the foundation of a lot of electromagnetic spectroscopy. Second item for us now is to take a look at how to acquire these oscillatory signals and what we can do about them, because it's a non-trivial procedure. There are several questions you can ask there. You can say, well, okay, how many points do we need per unit time? Because we can acquire a point every microsecond, every millisecond, every second. How many is enough for a signal that contains particular frequencies? Secondly, of course, when we acquire it, we will get noise as well as data. You've seen a little bit of that in the previous lecture, but a valid question is, okay, how do we get rid of the noise? In view of the properties of the Fourier transform that we have seen in the previous lecture. Firstly, digitization. So item 2 for today is sampling and something called Nyquist condition. Imagine we have an oscillation, some amplitude as a function of time, and that is our signal. The instrument only acquires it in a discrete form. It will put a point here, a point here, a point there, and so on. And the way I'm drawing it, it stands to reason that this signal would be pretty well digitized. We would always be able to reconstruct this sinusoid if we do know that it's a sinusoid and we have this list of points. Now the question is, how many are too few? And the Nyquist condition says we need a minimum of 2 points per period. So 2 points per period. And not just of any frequency, but of the fastest frequency that is present in the signal. Of the fastest frequency. Let us look at what is going to happen if we violate this condition. So here the period is roughly from here to here, right? It is decaying, but the period is about this. Let me put fewer points than 2 points per period. Let's say I will have a point here, so square, and then I will have a point there, and I will have perhaps a point here. And then I try drawing a signal through them. Obviously, the frequency would be wildly incorrect, so we will have something like that. Not even a frequency, right? It will be misjudged by the instrument. It doesn't have sufficient information to reconstruct that. And Nyquist demonstrated in his famous theorem that if you do have 2 points per period, you can reconstruct the signal with absolute accuracy, assuming you have enough decimal places there. What is this going to mean in practice? Imagine we have an NMR spectrum with a bunch of peaks in them, so something like that, and this, and you've got signals here, and maybe signals there, and signals here. This is how it looks. If we do sufficient digital sampling, so let's say here we have some frequency omega max, and here we have some frequency omega min, and there perhaps is 0, then, okay, what is the largest absolute frequency? In this case, omega max. And if we do take at least 2 points per period of that frequency, we're okay. However, if we do fewer, then let's say that is the sampling frequency that we have, and that. What will going to happen is these high frequencies, in much the same way as it had happened there, will be misrepresented as low frequencies. And as you can see, the phase of the frequency is of course also pretty much random. So what will happen is all of these signals will appear in a distorted form inside this frequency window which we did digitize. They will be looking, you know, up and down. Their complex phase will be twisted. So that is essentially a really bad idea to undersample your data. So whenever you are recording an oscillatory signal, decide for yourself what is the maximum frequency you could reasonably expect in that signal and digitize it with at least 2 samples per period of that frequency. NMR spectroscopists do get caught out with this, even the wise ones. You know that chemical shifts in NMR for protons range perhaps from 0 to about 10 ppm, which is the normal chemical range. But of course there are really exotic molecules. There are paramagnetic systems, there are lanthanides, there are various aromatic shielding anisotropy effects. Occasionally you can see negative chemical shifts for hydrides because there's so much electron density on H-. It might signal at -5 ppm. And the absolute record that we have seen was a signal at -10,000 ppm. And that was a hydrogen that was directly bonded to iron 2. Which was hugely paramagnetic, and it threw it as far as there. And then, of course, what you're going to see is a signal with a weird phase, and then expanding and expanding and expanding. The sweep widths, digitizing it better and better and better, would eventually put that signal where it's supposed to be. Okay, so this is the sampling of time domain signals. As chemists, you will encounter a ton of them outside magnetic resonance context too. Let us take a look at the frequency domain sampling, and that's called digital resolution. Digital resolution, and an interesting technique called zerofilling. Firstly, digital resolution. What we normally do with the NMR spectra that we acquire, certainly what organic chemists would often do, is integrate them. Because we know that the integral of the NMR signal is a measure of concentration, and all other things being equal, a measure of how many protons of a particular type the signal contains. And so once again, if we have some NMR signal that might have a shoulder or something like that, then it does matter how many points we have in that signal. Because of course what the computer is going to do ultimately is integrate this thing numerically by, for example, trapezium quadrature or something like that. So it will digitize it, and then it will draw straight lines between these points and approximate the signal integral as the sum of the areas under the corresponding polygons. You've all been through the elementary numerical methods module where such processes were explained to you. So little areas of these slices are summed up, and this is your integral. However, if we take the same signal and we digitize it badly, in the same way as here, but we would have too few points, this time in the frequency domain. So let's say we have a point here, and a point here, and a point there, and there, and there. And let's think about what is going to happen when the instrument tries to integrate this thing numerically. It will draw a line here, a line there, a line there, there, and there. And it will try approximating the total area as a sum of the areas of these individual slices. Well, it's pretty obvious that it has missed a giant chunk of area here. It has added an area that doesn't exist by cutting through. So this would be quite erroneous. And so what is necessary is to also digitize the signals adequately in the frequency domain. There are no rough and ready examples or conditions for this, not the ones that we can derive quickly in this module. So essentially the recipe is increase the sampling until the answer stops changing. When your integral is changing, when you add more points, that means you don't have enough points. Add more and more and more and more. At some point, the answer will stop changing. This is called convergence in mathematics, and then we are good. Now, how would one proceed to change the number of points in this frequency representation? Imagine we have a time domain signal which we have recorded, and it has decayed, and everything's good. So t, and this is f of t, and its Fourier transform are these signals. Turns out, and I will not prove this statement formally, it's a bit of a long story, that in order to improve the sampling in the frequency domain, it is sufficient to just pad the time domain signals with zeros. So if we take the signals that we had and we just add a long string of zeros at the end, what will happen is the frequency domain representation will get neatly interpolated and the accuracy of quantification there will improve. This is called zerofilling. I have given a few equations in the handout that describe the process formally, but as you can see from equation 9 of the handout, those are not the prettiest equations in existence, and so we will skip the formal derivation because otherwise it's quite easy to get terribly confused. The final thing that I will look at is something we had touched upon in the mathematics lecture already, that is digital filters. Remember what we saw there. We had a signal which we knew for a fact was varying slowly. And we saw a lot of fast noise on top of that signal. Well, clearly the noise has incorrect frequencies, and what we can do with it is we can filter it out. How would one proceed to do that correctly? Well, firstly, let us define what we seek to accomplish. Let's say we have some noisy signal. So that is some amplitude as a function of frequency. That is frequency. And we have some terrible noisy, but a peak. So clearly something here, but with lots of noise on top of it. One thing that we can attempt is called a local averaging filter. What I will do is I will take a bunch of these points, so the point here, the point here, the point here, the point there, and so on, and I will average them out. So I will say, okay, I take this point in the middle with a high statistical weight, points on the side with slightly lower statistical weight, and points far to the side with very low statistical weight. I average them all out and I put 1 point into the answer. Then I shift this entire picture 1 click and I perform another such averaging round and I put another point into the answer. Then I shift the bell again a little bit and I put the 3rd point into the answer. This is called the local running average filter. And let us think about what this corresponds to mathematically. Of course, this sum over these local points in mathematical terms is an integral, right? A discrete representation of an integral. This shifting bell is moving from point to point, and we acquire some filtered signal. So the filtered signal, so f of omega, is going to be, well, clearly an integral because we integrate. We don't care about the wings of this peak. They're 0 anyway. and so we can have an integral from -infinity to infinity. We do have the original signal here, so let's call this f. And on the output, we already have the symbol omega, so let's use nu here for the frequency. And we have our bell here, and I will call it g of omega. And the bell is shifted to where we want it to be, right, relative to the frequency there. So we would have g of omega minus nu. d nu in this case, because omega is returned. Another convolution, right? For that reason, this is called a convolution filter. And of course, what is going to happen is when we apply that convolution filter, the result will be significantly denoised. So this is our f of omega. That is the result of the process. And what we are going to have is some reasonably wobbly baseline with the remainder of that noise and a slightly broader signal, which, however, has been denoised. And this is something that you see a lot everywhere. Even if you are operating a radio telescope looking for aliens in the nearby galaxy, what is going to turn up in your detector is a signal with a ton of noise. The convolution filters are commonly used to reduce that noise. Okay, this was the picture in the frequency domain when we are looking at it from the point of view of the NMR spectrum. What would happen in the time domain? I had told you in the previous lecture, right, the properties of the Fourier transform, that the convolution operation in the frequency domain amounts to a multiplication operation in the time domain. And remember, what we also did is we did a Fourier transform that gave us a bell-shaped curve. Remember what it was? We Fourier transformed a decaying exponential, right? And we got in the output of it, so after a Fourier transform, we had a bell shape. So if there's no frequencies, then we would have a bell shape at 0. So in order to accomplish such a transformation, we therefore just need to multiply our time domain signal by some decaying function. And there's a mathematical meaning to that, and there's a physical meaning as well, as you will now see. So let us take a look at a typical NMR signal that turns up in our radio frequency coil as the signals are acquired from the precessing nuclei. It will be a decaying oscillation, and there will be a lot of noise in it. Typically, for the concentrations that chemists have these days, that is the case. Okay, so consider a noisy free induction decay. So this is our f of t, and that is time, and we will have some decay to 0. And on top of that decay, we will have a ton of noise. So something like that. More importantly, this noise will continue even after the free induction decay has finished decaying. Let us think about what would happen here if we were to Fourier transform this unchanged. So ft, and that is our f of omega, and that is our omega. We will have that noisy peak. So lots of noise and a noisy peak at some frequency omega naught, which was the frequency here. But think about what can be done here. We have lots of unproductive noise. This noise extends beyond the time area where all of the information was contained. It gives us no extra information about the frequencies that are present in this signal. It's just noise. So if we Fourier transform that unchanged, all of that noise will end up here. Then, of course, that convolution filter gives us an inspiration. It says, well, okay, if we multiply our signal by a decaying exponential, that is equivalent to this convolution filter. Well, let's do that. If we apply a decaying exponential here, what will happen is these parts that contain frequency information will survive, but the parts that simply contained unproductive noise will be multiplied by 0. So overall amount of noise in the data will be reduced, but the information content will stay largely the same. The result, if we do that, will be the signal that has been filtered. So f of omega and omega. So it will look something like that. It will be slightly broader. I will not go into the details of that, but it will be substantially denoised. And this is one of the things that as practical chemists you should be aware of when you bring your sample into the NMR facility. The people running that facility will do their best to apply this transformation. It has a name, it's called apodization. Or, in the frequency domain language, convolution filter. But they wouldn't spend too much time on it, because they've got plenty of samples and they don't have the time to fiddle with every one of them to maximize the signal-to-noise ratio. It is upon you, when you receive your magnetic resonance data, to play with these digital filters to get your signal-to-noise ratio to the maximum possible value. And that can occasionally be quite dramatic. Imagine you are dealing with carbon-13 or nitrogen-15, and typical lengths of the FID there can be many seconds. And so the instrument will naturally acquire many seconds of data. But if your relaxation rate, if your signal decays very quickly, then you only need the first 100 milliseconds of the data, and the rest will be noise. In that case, applying that filter would easily quadruple your signal-to-noise ratio, and I've seen that many times. For low concentration samples, that is a life and death kind of difference, because you will see some distant quaternary carbons that would not otherwise have been visible in your spectrum. Okay, so the summary of the lecture. These are necessarily quite technical properties that I've gone through. So the linear time-invariant system and its response to pulses and monochromatic perturbations. But this is central to all spectroscopy and much of engineering, right? And the outcome of our discussion is indeed we are certain now that we can do pulsed spectroscopies because the frequency response of a physical system is the Fourier transform of its pulse response. So that, I think, is the last piece of highly technical mathematics. We go into proper, interesting NMR from now, so you can be slightly less bored there. But as you can see, this needed to be done because it lays out the algebraic and to an extent computer science foundation of how modern magnetic resonance operates. Any questions? No? So in your handouts at the last page, you have a few Fourier transforms that I would like you to do.